In the last lecture, I talked about the double slit diffraction and interference pattern. So over here you can see an animation. You have plane waves coming in. There are two slits here. So you start to get diffraction, which is spreading of the wave, and then they start to interfere. You have interference pattern. Okay, in this region here, where you see the waveform, right? This is having a region of constructive interference. Then somewhere here in the middle, you don't see anything. It is because destructive interference, and so far so on. Okay, in the last lecture I also talked about the Young double slit experiment. So this was the setup. We saw on the screen the bright spots. In between you have the dark spot. Okay, I also derived the equation, and then I mentioned that the D, right, is usually very big. It is of the order of 1 meter, and the small d is of the order of fraction of mm. So if you compare small d and big D, the big D is about 10,000 times bigger than that of small d. And it is valid to say that these two rays are almost parallel. Angle theta is indeed very small, okay, because of the dimensions here. Okay, then in this animation, I illustrate to you the central bright fringe and the end order bright fringe. Okay, when you were to change the distance d, okay, you can see two slits here. The two slits are moving further apart. Moving further apart, the small d will increase. Coming closer together, small d decrease. So let's take a look at what happens when the small d decreases. So you can see that the fringes are further apart. So the distance from the central bright fringe to the end of the bright fringe increases. Okay, so this is still under two source interference. But because I couldn't finish it in the second lecture, that's why it's brought forward here. Okay, so similarly, same thing here, the fringe separation, distance between the two bright fringes is also affected by the small d. Then we look at the Young double slit experiment, an example on Young double slit experiment. Okay, so same thing, you take some time to do this question. Okay, assuming that you have already completed the question. So now let's take a look at what is given here. You are given a two slits interference experiment, okay, which is used to determine the unknown wavelength of laser source, as shown in the diagram. Okay, with the slits 0.2 mm apart. Okay, so before I talk about the two slits, you can see there's a third slit here. This is to ensure the coherence of the light waves when it reaches the two slits. So the two slits, small d is given as 0.2 mm apart. The screen is 1 meter apart, so that is a big D. The third bright fringe from the central bright fringe, so that is your yn. In this case, n equals to 3, so your y3 is 9.49. Part A, you are asked to find the wavelength of the light. So with the information given, to find the wavelength of the light, I need to recall the equation y3 will be equals to 3 lambda big D over small d. Make lambda the subject. With that, you calculate the wavelength of the light. Okay, wavelength of the visible light is in the range from about 4.5 to 7.5 times 10 to the power minus 7 meters, or about 450 to 750 nanometer. Okay, 400 to 750, around there. So if you get an answer within the range of visible light, you can be quite sure that you didn't make any mistake in the calculation. Okay, let's take a look at part B. How far apart would the slit have to be so that the fourth minimum, that is the dark fringe, would appear at 9.49 mm from the center of the screen? So now the distance that means the distance between the bright fringes changes, because instead of having a bright fringe here, now at 9.49 you are supposed to have a dark fringe, and it should be the fourth minimum. So if you remember, just now we said this is the first order, this will be the second order dark fringe right in the middle, third order dark fringe, and the fourth order dark fringe. Okay, so the distance between the fringes actually decreases. So before you do any calculation, you should know that the small d should also decrease. the small d should increase because the y is inversely proportional to d. Okay, since my y decreases, so the big D should increase. Okay, I let y prime be the new fringe separation, so and the d prime be the new slit separation. You are told that the fourth order dark fringe, right, is now at a distance of 9.49. So the distance from the middle to the dark fringe here now is 9.49, no longer this. So that means the new y3 prime, this is the distance from the central bright fringe to the third order bright fringe, plus half delta y, it must be equals to 9.49 mm. Okay, then I substitute in y3 is 3 lambda d, big D, but the small d changes, so I call it d prime. Similarly, on the other side, delta y will be lambda big D over d prime. Okay, then I make d prime the subject, I get the new d, which is 0.233 mm. So it has increases. Okay, because the distance between the fringes now gets smaller. So with that, I completed the two source interference. We move on to single and multiple slit diffraction. So right here, I will only be talking about single slit diffraction. When you have a plane wave passing through a single slit, this is the pattern that you get. Okay, instead of giving you spots, right, I'm giving you intensity versus the position. So right here, this region, you see high intensity. That means here you see a bright spot. Okay, here the intensity is 0, so you see a dark spot. And then you see some intensity of light, you see another bright spot. So when you pass a beam of light through a slit, you get interference pattern. Bright, dark fringes. And for single slit, we follow this equation. A sine theta equals to lambda, where A is the width of the slit here. Theta is the angle between the straight through position of the wave and the first order dark fringe. Okay, so this is the dark fringe, the first dark fringe, this will be your theta. Lambda is the wavelength. Okay, this equation is derived from wave theory. Wave theory is not required in your syllabus, so we will not go through the derivation. Okay, however, I would like you to watch a video in order to fully understand how come, okay, even when you have one slit, okay, you only have one beam of light, how come there is still interference pattern? Usually we need two beams of light to have interference pattern, but single slit can also spread and give you interference pattern. Okay, so you'll watch that video, which I'll not show it here. Okay, so you refer to the another section. I would like you to take a look at this equation again. Remember, we talked about single slit diffraction in the third section. So we were saying that there will be spreading if, okay, the wavelength is comparable to the width of the aperture. Notice that when the wavelength is comparable to the width of the aperture, okay, your theta is going to be big because your lambda over A is going to be big, and therefore there will be a lot of spreading. What happens when your wavelength is very, very small compared to A? Then your lambda over A will be a very, very small value, and your theta will be very, very small, so there is hardly any spreading. Now let's take a look at the situation. What happens if the wavelength is much larger than the A, the width of the slit? If that's the case, there's no theta. Theta is undefined. So what happens? That means there will be infinite spreading of the wave. It will spread the whole region because theta is not defined. So you have the maximum spreading here. Okay, so the video, right, you can go to this link to watch it, or I have actually downloaded it. You can also watch it. In this slide, I actually compare what you will see on the screen if you are using one slit. So you see bright dark fringes. Okay, in two slit we call it interference pattern, but in single slit we call it diffraction pattern. But they are referring to the same thing. Okay, basically bright dark interference patterns. Okay, but single slit is called diffraction pattern. So here you see the image is not very well, the spot is not very well defined. But when the number of slits increases, the spots are more and more defined. So that is the difference between one slit, two slits, and many slits. Resolution of single slit. Here I'm referring to two sources with passing through a single slit. This single slit, the application would be like a telescope. You can imagine these two sources as two stars that are very far apart, and the lens on your telescope will be your slit. So the light from S2, the star S2, will pass through the telescope and produce a diffraction pattern. Same thing for the light from S1, it will produce a diffraction pattern. And applying the principle of superposition, this is what you see. So on the screen, okay, on the telescope, what you see will not be blue light or blue spots or blue star. Okay, you won't see red also, you will see purple. So because you see there is a high intensity here, so you should see a very bright purple spots here. The intensity is quite low, so you might not see any light at all. Intensity here is very high again, you might be able to see another bright spot. Okay, so from the interference pattern, we know why we see two bright spots. Then at the side here, you can see there's some interference, so you might be able to see something, okay, some blurring images at the side. So you are still able to distinguish the two stars. Let's see what happens if I were to bring the two stars closer together. So same thing, they will produce their own interference patterns. Then use the principle of superposition, I get the interference pattern. Do you think you can still differentiate the two stars? Okay, for that, right, we will need to see how exactly it looks like on the screen. Well, I can see, if the star is round in shape, I can see probably there's one object here. Something that looks like figure of 8. So it suggests that probably there is another star here. So, well, at this instant of time, I can still figure out that there are two stars, but not very sure. Okay, but likely to be two stars because I get a figure of 8 instead of just one circle. So this criteria is what we call the Rayleigh's criteria. Rayleigh's criteria refer to the minimum separation for the two stars such that we can still tell them apart. But I'd like you to be familiar with this angle theta. It is no longer the same when we are using one source just now. Okay, for two sources, the angle theta will be defined by the two beams of light coming out from two sources. Okay, so this is the angle theta. From the angle from the first beam and the angle from the second beam is the angle between the two beams. Okay, this is what we will see, what we saw just now. Okay, if the two are very far apart, we see two spots. If they are just resolved, then probably we can figure out they might be two but not very convinced. But if they are any closer, we only see one circle, or we are one circle, right? We can't resolve them anymore. So the minimum condition for them to be resolved, for you to be able to tell them apart, will be the Rayleigh's criteria, which states that when the central maximum of one pattern, one diffraction pattern, falls on the first minimum of the other image, we say they are just resolved. Okay, so this is the condition. Central maximum of one pattern, will be the red one, falls onto the first minimum, the blue one. Okay, then they are just resolved. And from wave equation, the wave theory that I showed you just now, A sine theta equals to lambda. So we get the minimum angle, assuming small angle, the minimum angle for you to resolve the two stars or the two objects will be when your theta minimum equals to lambda over A. Okay, how do I get this equation? using small angle approximation, sine theta will be approximately theta. Bring the A over. So the minimum angle between the two stars must be lambda over A. Then you can just resolve the two stars or the two objects. Okay, with that, I come to an end for single slit.